Lab 26, Tock Iodine Clock. Introduction. The reaction used in this experiment is a classic example of a chemical clock. The term chemical clock refers to a reaction where the concentration of one of the chemical components undergoes an abrupt change in concentration after a time period and leads to a sudden change in color. The reaction in this experiment is termed an iodine clock reaction because it is the molecular iodine, or I2, that undergoes the sudden concentration change. When the iodine concentration increases, it reacts with the starch in the solution to form a complex, turning it a deep blue-black color. And we have the equation here for you, which is the aqueous form of molecular iodine plus starch is going to lead to a triiodide starch complex, which is a deep blue-black color. The iodine clock reaction is a classical chemical clock demonstration experiment to display chemical kinetics in action. It was discovered by Hans Heinrich Landholt in 1886. The iodine clock reaction exists in several variations, which each involve iodine species, either iodide ion, free iodine, or iodate ion, and redox reagents in the presence of starch. Two colorless solutions are mixed, and at first there is no visible reaction. After a short time delay, the liquid suddenly turns a shade of dark blue due to the formation of triiodide starch complex. In some variations, the solution will repeatedly cycle from colorless to blue and black to colorless until the reagents are depleted. The materials needed for this lab are distilled water, ascorbic acid, more commonly known as vitamin C, Lugol solution, which is also known as iodine solution, hydrogen peroxide, soluble starch solution, pipettes, 50 milliliter Erlenmeyer flasks, 50 milliliter beaker, 10 milliliter graduated cylinder, test well plate or strip, and a stopwatch or timer. Procedure, Part 1. Measure 50 milliliters of distilled water into an Erlenmeyer flask. Add your quantity of ascorbic acid to the flask and swirl until dissolved. Measure 10 milliliters of your ascorbic acid solution into your graduated cylinder and pour it into your beaker. Label an index card Solution A. Place the beaker of ascorbic acid on the index card. Procedure Part 1 continued. Observe the color of the Lugol solution. Lugol solution is a dark reddish-brown color. You're going to add 10 milliliters of the Lugol solution to the beaker and observe the color of the combined solutions. When the red-brown Lugol solution is added to the ascorbic acid solution, the combination of solutions are clear and colorless. As you'll see in this lab, while Lugol solution is a good indicator for the presence of starch, it also turns clear in the presence of certain acids. Ascorbic acid serves as a reducing agent and reduces the iodine in Lugol solution to iodide ions, which are colorless in solution. When ascorbic acid reacts with iodine, the ascorbic acid is oxidized, it loses electrons, and the iodine is reduced, or it gains electrons. As long as the solution contains ascorbic acid, the iodine is used up in a rapid reaction with ascorbic acid, during which dihydroascorbic acid and iodide ion are formed. So first, ascorbic acid, like most acids, will dissociate in water and produce some hydrogens. The Lugol solution will also break down in the water and we will get some free iodine. Some ascorbic acid will react with Lugols, and we will also have ascorbic acid and iodine together, which will result in the oxidation of the ascorbic acid and the production of iodide. Procedure Part 2. Rinse your graduated cylinder with distilled water. Measure 10 milliliters of the distilled water into your graduated cylinder and add it to your second Erlenmeyer flask. Then you're going to measure 10 milliliters of hydrogen peroxide into the graduated cylinder and add it to the Erlenmeyer flask. So next you'll add 4 milliliters of soluble starch solution to your Erlenmeyer flask. So now your Erlenmeyer flask contains distilled water, hydrogen peroxide, and some starch solution. You're going to swirl this until it's very well mixed, and you're going to label an index card Solution B. Place your flask of hydrogen peroxide and starch solution on the index card labeled Solution B. And observe the color of this solution. So as you can see, Solution B is clear, but it's a little bit more cloudy than A. Both are colorless. So in part 1, we evolved iodide, and we did also evolve some iodine. Now we're about to evolve more iodine by using our new solution to combine with our first solution. So some iodine is now present as well as some iodide. So some iodine is now present along with some iodide. Using iodine to test for the presence of starch is a common experiment. A solution of iodine, or I2, and potassium iodide, which is Ki, in water has a light orange-brown color, and if it's added to a sample that contains starch, the color changes to a deep blue. So how does this color change work? Starch is a carbohydrate found in plants. It consists of 2 different types of polysaccharides that are made up of glucose units, which are connected in 2 different ways. One is a linear amylose, and the other is a branched amylopectin. See the graphic over there to the right. Amylose is the compound that is responsible for the blue color. Its chain forms a helix shape, and iodine can be bound inside that helix. The colors are caused by so-called charge transfer complexes. Molecular iodine is not easily soluble in water, which is why potassium iodide is added. Together they form polyiodide ions, and these are of various types. They can be ions of I N negative, I3, I5, or I7 negative. Negatively charged iodide in these compounds acts as a charge donor, and the neutral iodine as a charge acceptor. So basically, you have electrons in such charge transfer complexes that are easy to excite to a higher energy level by light. And then the light is absorbed in a process, and its complementary color is observed by the human eye. In the case of aqueous solutions of polyiodides, the absorptions of different species lead to an overall brownish color. But once amylose is added, it forms another charge transfer complex here, and the amylose acts as a charge donor, and the polyiodide as a charge acceptor. And this complex absorbs light of a different wavelength than the polyiodide, and it turns a dark blue color. So how does the concentration affect the rate of charge transfer complex formation? Procedure Part 3. So we're going to place the test well plate on a second index card. And we're going to use a clean pipette and carefully transfer drops of solution A and distilled water to the test wells as follows. So as you can see, we have 5 drops of solution A to 20 drops of water in test well 1, which is rather dilute. And then test well 5 is just 25 drops of solution A and no drops of water. So our dilutions are greater to the left and more concentrated towards the right. We're going to copy down the data table below. And as we continue part 3 of our procedure, this is where we need a team effort. So we needed to borrow members from other teams, and the goal is that as quickly and as simultaneously as possible, you need to add 3 drops of solution B to each of the 5 test wells while simultaneously starting your timer. One teammate must watch the test wells carefully for color change. A second teammate must watch the timer, and a third teammate must record the data in the table.
2 and then 3.
This one, that was going
0, 1, 2,
33 for that one.
Cool.
I'm so sorry, guys.
Okay. It's fine. Nothing's happened yet.
Yeah,
Make sure Cole can see because he has timer.
37.
Don't pause it, Cole. Just tell me what it is when it happens. Keep them all right here.
Middle one was actually the last one.
15 seconds.
Okay, first.
Oh, there's some blue in the first.
First two.
In well 1,
There's some blue in the next one.
Yeah.
Yeah.
At 17 seconds.
There's blue right there. They all have blue in them.
That's all of them 30 seconds, 31.
This one has a little blue in it. That's just really close. Oh, whoa.
Mine's
Mine's like completely black.
Nice. Look at that. Very nice.
The main one's only black on the top, but this one's super black.
This is the order in which they went.
Cool.
This is the times. No, that one.
Do I get
Wait,
All right, Drew, are you trying to get in there?
Drew.
Don't pour it yet, don't pour it yet, don't pour it yet.
Move over.
Pedal it.
Okay.
Switch Drew.
You go around.
Drew, this is gonna go great.
I know.
148.
You start.
1, 2, go. There.
I don't think I put my last one. Way more than 3 drops. No, I put 3. No, we put 3.
He told me he put 12 in ours. I'm pretty sure he just dropped it all and didn't count.
Yeah, he's like.
That one's turning, I'm gonna say 7. No, that's too faint. That one's turning 17, or 18, sorry. Okay, 18. 22. 18 and 22.
18, 22.
27.
27.
30. That one was first.
30.
That one turned, okay, 40.
Oh my God.
Sorry, 35.
Look at that.
Okay, so
40 and 35. I don't know what I'm doing. Okay, what was that?
There's anything in the dropper that'll drip.
Make sure you have a.
Left, right, please.
Alright, but get over there. Helio. Yes, you can have it.
What's the 27?
Bring this back out 4.
1, 2, 3.
Live. Okay, no, put them over here on this board. Alright, Cole, tell me the timestamps. Or make sure you're, Bailey, make sure you write down what Cole's saying. Cole, what time is it?
15 seconds.
15 seconds, test tube 1 has some blue residue. What time?
21.
21, test tube 2, a little bit. At, what is it?
25.
25, test tube 4 has more than test tube 3.
22
Good observation.
for the next one. All right, 18.
Time?
33, going first is black.
Yep. Number 1 is black on 33.
Then look at
Is number 2 black?
Not quite yet.
21 it is.
Yeah, it's not yet, but yeah. Still nothing in number 1.
Yeah.
Not number 1,
We're
in number 5.
53 seconds now.
What?
53, 55.
It's almost.
It's a minute.
Lastly, complete your data table. So here's our data table, and these are our class average figures. So let's chart it, make it a little easier to see. So test well 1, 2, 3, 4, and 5. Data and analysis. Which combination of volumes reacted the fastest and the slowest, and why do you think this was so?
So we had to evolve. If you look here, this was how we get a color change. And we had to try and evolve as much elemental iodine as we possibly could. And some of that occurred in the second reaction. So as far as which one of these was likely to finish last or finish first, this one had less elemental iodine to begin with, right? Because it had less of its solution A to solution B. We had a lower concentration here. This was way more dilute because it was 5 drops of solution A to the 20 drops of water. So because of that, it finished more quickly. It didn't have as much to do, basically. And in this case, it took longer because there was more of it to be consumed. Does that make sense? All right, does anybody have any thoughts on that, or?
What are some possible sources of error, and what procedural improvements could be made to help achieve more accurate results?
Okay, so then our last question to look at for lab was this one here. So what are some sources of error, and what are some things you could do to make the lab more efficient or get more accurate results?
So the biggest one was like, obviously we didn't all perfectly drop them at the same rate, just because it's not possible. So we need one of those connect 4 things where like you pull the tap and it all drops at the same
They
time.
all drop at the same time?
But with a titrate.
There you go.
One of those.
Yep.
And different sizes of drops, and Alex somehow squirted all of his in.
Yeah, that happened.
Finished
I
last.
probably want to help.